An insulated non-conducting rigged tank contains 25 kilograms of liquid water at 20 degrees Celsius. A paddle wheel inside the tank is driven by a 35 kilogram hanging mass that descends slowly by 5 meters while turning the paddle. Assume all of the gravitational energy lost by the mass is transferred to the water, and take G is equal to 9.8 meters per second squared. Determine the work delivered to the water, the change in internal energy of the water, the final water temperature using Cp is equal to 4.18 kilojoules per kilogram Celsius, the heat that must be removed to return the water to 20 degrees Celsius, and the total energy change of the universe for the lowering/stirring step, the cooling step, and both steps combined. Our system is the water in the tank. This is a closed system, meaning that mass does not cross the system boundary, and the tank is insulated, meaning that there is no heat transfer. So our heat Q is equal to 0. The paddle does work onto the water directly, which increases the water's internal energy. For part A, we are asked to find the work delivered to the water. So the work delivered to the water is equal to the mass of the weight times the gravitational constant times the distance that traveled. So plugging in, we have our 35 kilogram mass times our gravitational constant of 9.8 meters per second squared, then times the distance that it falls, which is 5 meters. This tells us that the work delivered to the water is equal to 1,715 joules. Or if we divide this by 1,000, we get that that's equivalent to 1.715 kilojoules. For part B, we can use a simplified form of the first law of thermo, which is that our internal energy is equal to our heat plus our work. Now our heat is equal to 0, so our internal energy of the water is just equal to the work done to the water, which is equal to the 1.715 kilojoules. Now to find the final water temperature, we can use the equation that the internal energy of the water is equal to the mass of the water times the heat capacity of the water at constant pressure times the change in temperature of the water. Solving for the final temperature, we can divide the internal energy by the mass of the water times the heat capacity plus the initial temperature. So solving this, we get 1.75 kilojoules divided by the mass of the water, which is 25 kilograms, times the heat capacity, which was 4.18 kilojoules per kilogram Celsius, plus the initial temperature of the water, which is 20 degrees Celsius. Here we can make sure our units cancel. The kilograms cancel here, and kilojoules cancel here to give us Celsius, giving us our final temperature of 20.0164 degrees Celsius. Now for part D, to return the water to its original temperature, we have to remove the energy that we added to it. So this is just equal to the 1.715 kilojoules that we added. For part E, the total change of the universe is meaning the system plus the surroundings. Energy can be moved inside of this system, but the total energy is always conserved. So the change in energy of the universe is equal to 0 for all of the steps.